Hello, Prof. Together with my team, Christina, Aaron, Tristan, and Mark, we will be presenting our Data Analytics as a Service cloud computing project hosted on AWS. Our chosen dataset is created from MOE, which is related to the Graduate Employment Survey from the different Singapore universities. As such, our DAAS platform will analyze graduate employment trends and patterns. We do not see a centralized interactive tool such that it analyzes salary trends and employment rates after students graduate from their respective universities. With that, our solution is to come up with a cloud-native DAAS web application deployed on AWS Elastic Beanstalk. Our platform allows users to analyze trends, compare salary and employability sweet spots among different universities, as well as a predictive model that forecasts future salary predictions using linear regression models. Our cloud software stack for our DaaS platform are designed using core AWS services, adopting a platform as a service cloud service model. By choosing this model, our team can focus on the development front-end datasets, leaving the network infrastructure and runtime configurations to be facilitated by AWS. This PaaS approach provides an optimal balance of control and convenience, reducing operational overhead while still allowing the application to scale reliably as needed. For our software stack, AWS Elastic Beanstalk is used, which also automates infrastructure management such as scaling and load balancing, allowing us to focus on app logic while ensuring scalability and cost efficiency. For computing, EC2 instances are deployed with auto-scaling. Auto-scaling adjusts compute resources based on demand while ensuring consistent performance and minimizing costs during low traffic. For storage, S3 is used, which provides scalable and durable, cost-effective storage for our processed dataset. Virtual Private Cloud is used for networking to secure the web app components by isolating them in a private network with controlled access and high-performance routing. In application delivery, Auto Load Balancer helps to distribute traffic evenly across instances, enhancing availability, reliability, and fault tolerance. Lastly, for monitoring, CloudWatch is used to monitor our web app performance in real time, triggering auto-scaling and alert for proactive issue resolution.
Hi, my name is Christina, and I'll be talking about two of our functions. Firstly, trend analysis. This feature tracks the historical trend of outcomes for a selected university and degree, specifically employment rate, full-time permanent employment, and median salary. After the user selects the filter, we aggregate the data by year, calculate the year-on-year change, and apply a 3-year moving average to smooth out short-term fluctuations. On the left, the charts compare the actual yearly values with the moving average, so you can quickly see the overall direction. On the right, the table shows the exact numbers, including year-on-year and moving average values for transparency. Overall, this helps user judge long-term stability and career value instead of reacting to one-off spikes or dips. Next is function 2, salary spread analysis. This feature measures income inequality and outcome risk within each degree program. Even if two degrees have similar median pay, one may be much less consistent. We calculate the interquartile range, which is the 75th to 25th percentile, to capture how wide the salary spread is for the middle 50% of graduates. We also compute an IQR ratio, which scales that spread against the median salary for fair comparison across degrees. The top table highlights degrees with the largest spreads and highest ratios, and the full table below provides reference. Overall, it helps user identify degrees with stable pay versus degrees with higher salary uncertainty.
My name is Aaron and I'll be talking about functions 3 and 4. Function 3 is comparative ranking, which helps user identify the top paying degrees across all university for any selected year. We start by filtering the dataset by year, then we sort all degree programs by gross monthly median salary. This gives a clear ranking from highest to lowest. We also calculate the rank change by comparing with the previous year, allowing users to spot emerging programs that are quickly rising in the salary competitiveness. Overall, this function provides a fast way to compare degrees between universities and understand how the performance shifts over time. Next is function 4, relationship analysis. This feature examines the correlations between employment rate and starting salary across all degrees. We plot employment rate on the x-axis and median salary on the y-axis to visualize how strongly these two factors are related. So from the scatter plot, users can easily identify two key groups. The sweet spot degrees, basically the programs with both high employment and high pay, and the niche degrees, those with high salary but lower employment rate. Overall, this function helps user understands whether the higher employability tends to lead to higher starting pay and highlights which degree offer the best balance between both.
Hi, my name is Tristan, and I'll be talking about our final function, simple projection, as well as our auto-scaling. So the objective of this function is to forecast potential salary outcomes for the upcoming academic year. And in order to do this, we apply a linear trend extrapolation model, which follows the equation y equals mx plus c. So we use the last few years of historical salary data to calculate the trend and then extend that trend to estimate the next year's salary. The key benefit of this function is that it gives students a data backend estimate of future earnings instead of just looking at past numbers. This helps them make more forward-looking and informed decisions when choosing a degree. Next, I'll talk about our auto-scaling strategy. Our system uses AWS Elastic Beanstalk's auto-scaling feature to automatically adjust the number of EC2 instances. A system maintains between 2 to 4 instances depending on CPU usage. If the CPU usage goes above 30%, the system will automatically scale up and add more instances, whereas if it drops below 20%, it will scale down and remove extra instances. This approach gives us three main benefits. First, performance, because the system can handle sudden traffic spikes. Next will be cost efficiency, since we only use more resources when needed. And lastly will be reliability, because traffic is distributed across multiple instances, reducing bottlenecks.
Hi, my name is Mark, and this slide summarizes our performance testing using Apache JMeter across all 5 of our analytical endpoints. For all runs, we kept the same test structure, 10-second ramp-up and 300-second duration, and only varied concurrency at 100, 200, and 400 users. We measured total throughput, average response time, error rate, and cross-checked CPU utilization from CloudWatch. Firstly, at 100 users, the system is stable with 0% errors, about 14.1 requests per second, and an average response time of 6.7 seconds, with CPU around 34.5%. At 200 users, average response time increases sharply to 15.3 seconds, while CPU utilization remains about 35.5%. That gap suggests performance is not limited by raw CPU, but more likely by application-level concurrency limits, request queuing, or maybe I/O waiting. At 400 users, the system still shows 0% errors, throughput is about 15.3 requests per second, but average response time rises further to 23.7 seconds, and CPU utilization is still only about 41.4%. So the key takeaway is the system remains reliable under high concurrency, but latency grows significantly, indicating the main bottleneck is response time growth rather than the compute saturation. Now on reliability and fault tolerance, we designed the deployment to minimize downtime and recover automatically. First, for high availability, our Elastic Beanstalk environment's auto-scaling group spans 2 availability zones, or AZ for short, so the application is not dependent on a single data center. If one AZ becomes unavailable, traffic can still be served by instances running in the other AZ. Second, we rely on a self-healing mechanism. The application load balancer continuously checks instance health, and when an instance fails the health check, the auto-scaling group automatically removes it and launches a replacement, which is reflected in the activity history shown. This reduces the need for manual intervention and improves service continuity. Finally, the application is designed to be stateless at the compute layer. Instead of storing important data on the EC2 instance, our dataset is stored in Amazon S3. So even if an instance is replaced, the application can recover without losing application data, creating redundancy. Overall, these 3 layers work together to maintain availability and fast recovery during failures.